To graph this function, we can't just use a common denominator, but I can use our division method. I thought I would use the matrix method again just for practice. So the x plus 1, x plus 1. My answer of 2x cubed needs to go here. So x times 2x squared. And then 2x squared times 1 is 2x squared. I need to make 7x squared here. Well, the 2x squared I have, if I add 5x squared, I'll get my 7x squared. X is still here. To make the 5x squared, the 5x has to be here. And then 5x times 1 is 5x. I have to make the next term in my answer is 7x. I have 5x here already. I need 2 more x to make the 7x. To make this 2x, I need a 2 here. 2 times x is 2x squared, 2x. And then 2 times the 1 is 2. To make the 5, I already have a 2 here. I need a 3 to make the 5. And 3 is my remainder. Now next we're just going to give you the graphs. Okay? So below, the red graph is the parabola, which is this part of the answer. And then we're just telling you that the blue graph is the original problem. So that here is the original problem, and that's the blue graph. So if I do the division, these two are the same. But for the red graph, I'm going to take off the remainder. Let me write the remainder here. 3 over x plus 1. As x gets bigger and bigger and bigger, 3 over big is smaller and smaller and smaller, which means as x gets huge, this remainder becomes almost meaningless, which means as x gets bigger and bigger and bigger, the graph starts to look the same because this part is meaningless. And sure enough, the ends of the graph start to look the same. The ends of the parabola and the ends of the blue graph start to almost overlap. In the middle, they're different, but the end behavior is very, very similar. And we just mentioned, here's the remainder. As x gets bigger and bigger and bigger, this fraction gets smaller and smaller and smaller, so that our polynomial and the remainder starts to behave just like just the polynomial without the remainder. Now there's an easy way to find the horizontal asymptotes of a polynomial function, a rational function, a polynomial over a polynomial. Okay? And since the first terms, if I write them in a certain way, always have the highest exponent, as x gets bigger and bigger and bigger, the first terms dominate because the x is to the highest power at the beginning. And so we can say that as x gets bigger and bigger and bigger, that's the idea of end behavior, right? at x goes to infinity or negative infinity. The first term dominates, and I can just look at it, and the rest of it I don't have to look at. So if m is greater than n, if the bottom exponent is larger than the top, then the bottom will dominate, and it's bottom heavy. Well, if a fraction is bottom heavy, if the bottom is bigger than the top, it's going to get bigger and bigger and bigger and bigger, and if the bottom of a fraction gets bigger and bigger and bigger and bigger, the fraction itself gets smaller and smaller and smaller, and so the horizontal asymptote is y equals 0. If the exponents are the same, then neither one dominates, but they're the same, and so the ratio of the coefficients becomes the horizontal asymptote. And if it's top heavy, if the exponent on top is bigger, then the top is going to go faster and faster than the bottom, and that's going to go to infinity, which means I won't go to a number, and so there will not be a horizontal asymptote. Now watch how easy this is. In A, the denominator's exponent's bigger, so it dominates. That's case 1 from above. And if it's case 1 from above, then it's bottom heavy, and the fraction gets smaller and smaller and smaller, and the horizontal asymptote is y equals 0. In B, they're the same. If they're the same, then in a way they undo each other, and it's just 4 over 2 is the y value, and the horizontal asymptote is the ratio of the coefficients 4 over 2. That's only if the exponents are the same, the degrees are the same. In example C, the top is bigger than the bottom, so we do not have a horizontal asymptote. That's all it is. So for this one, it's bottom heavy, so the horizontal asymptote is 0. We can see that the vertical asymptote is x equals -2. That makes the denominator 0. And let's see, x equals -2, y equals 0. That's choice 4. In B, the degrees are the same, so it's same. The ratio of the coefficients are 1 over 1, which is 1, y equals 1. To make the denominator 0, x is again -2. So 1, horizontal asymptote, -2 for the vertical asymptote. That's choice 5. In K, it is top heavy, so it has no horizontal asymptote. That's choice 2. If I look at just the coefficients or the first terms, 3x squared over x, that's like 3x. And we see this line with a y-intercept of 0 and a slope of 3. So that the graph looks like 3x at the ends. Here it's top heavy, and if I divide just the first terms of each, I'll get 2x squared. And the end behavior will look like a parabola, and that's choice 3. And here again it's bottom heavy, so the horizontal asymptote is 0. And choice 1 takes care of that for us. So all we have to do is look at the first term of the numerator and the first term of the denominator and compare them. If I take the two that didn't have a horizontal asymptote, so that would be this picture here, which was this one, K, and this picture here, which is this one, L, K and L. And in each of these cases, I did synthetic division. So again, as x gets bigger and bigger and bigger, the remainder goes away, and the graph will start to look like this line 3x plus 1 at the ends. So that if I go here, and this end and this end start to look like the graph. On the other hand, if I do synthetic division here, and again the remainder goes away when x gets bigger and bigger and bigger, the ends of the graph will start to look like a parabola. So sure enough, the ends of the blue graph will start to look like the red dotted parabola. We call this line a slant asymptote, and we call this second degree asymptote a quadratic asymptote because it makes a parabola.